So welcome, Marina and Denise. Welcome, Jack. And welcome, Roxy and Sophia Marquette, Jose, Luz, and Jacqueline. Thanks for coming. Um, let me share my desktop and we'll take a look at the quiz. Okay, so here's a quiz. And question 1 says, suppose you want to find an 80%. It says it's blank. Uh-oh. Oh, your last answer didn't save. Yeah, it should have saved. I can't, I'm not there, so I can't really, it's not the kind of thing I can do right here if something didn't save, but I'll take a look. So hard for me to know. But let me go through the quiz and we'll talk about it. So suppose you want to find an 86% confidence interval for the proportion of all Americans who are truly practicing safe social distancing. If you want a margin of error of no more than plus or minus 3%, how many Americans must you survey? Be sure to show your work similar to what was done in the webinar and not just give the final answer. All right, so the kind of what you want to start here is, what are we looking for here? What is the question asking? What type of question is this?
Sample size for proportions.
Yeah, so this is a sample size for proportions. Let me write that out. And let me explain, or help you all, those who didn't quite get it, understand why. First thing is, how many must you survey? That means, what is the sample size? That's just another way of saying what is the sample size. Then the survey question is, are you practicing safe social distancing? Okay, or maybe the observation, what you're going to be watching people and you're going to think and you're going to say, look at them, are they practicing safe social distancing? And the answer is yes or no, not 73 or something like that. So because it's a yes no survey question, we know that we're talking about proportions. Okay, not to mention there's a word proportion, but even more important, it's a yes no survey question. Any questions on that so far? Okay, so if it's a sample size for proportions, I always like to go through and look at the numbers that are given. We have an 86% confidence interval. So what does that tell us in letters?
CL.
Can you repeat the question?
Yeah, so what is 86% confidence interval? The letters for that are CL. And remember, you turn it in decimals, 0.86. And we want a margin of error of no more than plus or minus 3%. So what letter is that?
E.
E. Okay, is E equal 3?
No.
Yeah, you got to be careful. It's percent, and you always have to turn percents into decimals. So it's actually 0.03. Do we have a preliminary estimate?
No.
No, no preliminary estimate. Any questions on that? Okay, so now let's go to our calculator. And we want a sample size for a proportion. So that's number 13. And no estimate for P. E was 0.86. Sorry, E was 0.03 and CL was a 0.86. And I hit calculate N. Any questions at all on finding the sample size? 605. All right, so let's write it out. So we must survey 605 Americans. Any questions at all about finding the sample size in this case? Okay, let's move on to question 2. Question 2 is, suppose you want to find a 90% confidence interval for the population mean time it takes people to shop for groceries. If you want a margin of error of no more than plus or minus 0.5 minutes, and a preliminary study gave you an estimate of 7 minutes for the standard deviation of the time it takes to shop for groceries, how many people must you observe at the grocery store? Be sure to show your work. All right, how is this one different than the last one?
It's for the mean instead of proportion.
It gives you an
Mhm.
estimate.
Yeah, it's not that it gives you the estimate. Actually, that's actually not a giant difference. The giant difference is that we're talking about a mean. We're talking about a mean and not a proportion. So because we're talking about a mean, then what the calculator we need is the sample size for a mean. Any questions on that? And now we can look at our numbers and turn them into letters. 90% confidence interval. What does that tell us?
CL equals 0.9.
Yep. CL equals 0.90. Okay. And then you want a margin of error no more than plus or minus 0.5 minutes. What does that tell us? Yeah, E is equal to 0.5. Okay. And then we have a preliminary study gave an estimate of 7 minutes for the standard deviation of the time it takes to shop for groceries. Okay. So what does that tell us?
Sigma equals 7.
Yeah, that's sigma. The standard deviation is equal to 7. Any questions? Any questions on getting it all set up? Okay, now that I have it set up, now I go to which calculator?
Sample size for mean.
Yeah, sample size for me, number 11. And then we go ahead and our standard deviation, our sigma was 7. The E was 0.5. And the confidence level, the CL, 0.9, I believe. Let me remind myself again, but I'm pretty sure. Yep. And 8 calculate N. And you get 531. So in particular, we survey 531 people. Any questions at all on this quiz? Any questions? Okay, so
For once, I actually got things right.
what's that?
I actually got things right on this
Same
one.
here.
Getting things right is good.
Bravo! Proud of you, my friend.
Yeah, getting things right is good. Yeah, if you didn't save it, then yeah, talk to me in office hours. That's a one-on-one thing, not a helping everyone else kind of thing. So after class. Any questions at all on this? Okay, if there's no questions, let me move to questions about other things. Are there any questions about anything else in the class? And as you're thinking, I want to remind you of a few things. One, again, in 9 days is the exam. So definitely you want to start, getting ready a little bit for it. Okay, and the exam will cover up till the end of this week. I don't give you an exam on stuff you haven't had homework on yet. So it goes up through chapter 9.
I have a question.
Uh-huh.
How many exams do we have? Is this the second and last one and before the final?
Yeah. So there's 2 regular exams and 1 final exam. Okay. It's kind of weird. It's a little bit more than you get at university. And but if I only gave you 1 exam, that may, then it's a lot of material just for 1 exam. And it also takes a long time for you to actually find out how you're doing. So that's why I give 2 exams. Okay, and the final. And the final is comprehensive, whereas this one will not be comprehensive. But yeah, good question. The other thing I want to remind you on is the project, although you have a while for it, still, a few weeks down. But in terms of the project, number 1 is make sure you have partners. Okay, 3 is better than 2 in a partnership. But you definitely need to have partners. Otherwise, you can't pass, and not passing is bad. So make sure you have partners for your exam. Very important. And you don't have to have the same partners at project 1, but you have to have partners. So that's a big deal. Okay. And on Thursday is our day to talk about it. So I'm not getting into any details today. But I want to just let you know you need, scooping up partners are really, really important. Okay, so that's some big things coming up. Any other questions? Any other questions? Okay, if there's no questions, then I'm going to start getting into hypothesis testing. Okay, which you actually, whether you remember or not, you have had the idea of hypothesis testing already under a different name, different title, but you may not remember because it was a while ago. Okay, and I really mean a while ago. I don't mean months. And that is, do you remember scientific method? You get it in middle school. And you remember what the scientific method is? Sure, you remember the words. And you remember what that means.
Sort of.
Huh?
Sort of, yeah.
So what is a scientific method?
Where basically you have a question and you test and retest it until you can form a theory.
Okay. So the idea is what we're doing in this chapter, and pretty much for all the rest of the chapters, is a scientific method. So you've already had it, but we're going to do the statistics involved in the scientific method. So we're going to be looking at the statistical processes for the scientific method. And again, it's been a while for some of you. It's been a long while for others. And, some of you might have seen it recently in other things, but everyone gets it in middle school, or you're supposed to at least. And let me remind you on the processes. And I see in the chat box, hypothesis, test, observe. Okay. And that's kind of the idea. It's kind of the idea. Those are the 3 words you remember, or hypothesize, test, observe. So the very first thing is you hypothesize. Okay. And you come up saying, well, what's your idea? What's your thought? What do you think is probably true based on what you just kind of winged it? Okay. Just gut feeling. The hypothesis is a gut feeling. What you think might be true. You got the status quo, but you think things have changed a bit. Things are a bit different. Here's what I think is true. And that's your hypothesis. Then what you do is you say test, but for our class, it's collect data. So what you're going to do is you're going to collect data that will either support your hypothesis or not support your hypothesis. And that could be done with a survey. It could be done with an experiment. It could be done by observation. There's lots of ways of collecting data. Okay. Then what you do after you collect the data is you crunch the numbers. Okay. So you take that data, you crunch the numbers, to see whether or not your data will support your hypothesis, or maybe it doesn't support your hypothesis. And so you do that. And what we're going to do is we're going to find the probability that if the other hypothesis, what you're trying to show is not true anymore. If the other hypothesis was true, then you want to show that it'd be very unlikely to get what you got. So therefore, the other hypothesis must not be true. Okay, so that's the idea of hypothesis testing. Any questions on the idea? Any questions? All right, so what I want to look at now, I'm going to give you some kind of examples, kind of get more general idea examples, and then we'll do one, true formal example where we actually get it all with all the numbers and all that. But let me do an example that you might be able to relate to. Maybe you've done, maybe you haven't. Any of you ever served jury duty? Say yes or no. Either
Not yet.
have or you haven't, by the way. You can't kind of serve jury duty. Maybe you're all under 18, but I doubt it. Oh, I'm seeing all no. Maybe I'm unique. I'm older. I'm probably older too than all of you.
Feeling special.
Yeah, feeling old. I don't know. Okay, so, but even if you haven't served jury duty, hopefully you understand at least a little bit about what the court does. Okay, even if you haven't actually experienced it, because maybe you've watched it on TV or something. So let me kind of go through the court system, because the court system is basically hypothesis testing. So the first thing after they've picked you and told you they now own you for however many days or weeks that they've got you on the jury for, so they've picked you, and I was picked. I have been picked once actually. So they pick you, and then you sit on the jury, and then once a judge gives you instructions, what's the next thing that happens? What's the next thing that happens in court?
Repeat the question.
So what's the first thing? What's the first major thing that happens in the court once they've selected the jury?
They go to a room and discuss whether he's.
That's actually one of the last things.
The trial. The
The
actual
trial.
trial itself.
Yeah, but how does the trial start?
Each side delivers their piece.
Yeah, each side delivers their piece. And unfortunately for us, it's actually in the exact opposite order of hypothesis testing, at least the way we write it, but the order's not that important actually. So what happens is there are two cases. Imagine the prosecution and the defense, right? So those are the two cases. So I'm going to start, even though it's not quite right, because in real trial, this doesn't happen. I'm going to pretend that the defense gets the first, that they talk first. And what they do is they say, hey, my person's not guilty. Nothing weird happened. So I'll kind of imagine that the lawsuit is about some kind of food company, and there's a whole lot of people that died after eating their food. Sound good? Sound bad, right? So a lot of people died after eating their food, but the big question is, was the food company guilty of anything? And the food company's lawyer is going to say, hey, people die, people would have died anyway, 100,000 people ate the food and 20 people died, but 20 people might die anyway, right? So that's no different. It's not about the food. It's just people die. Don't blame me. Does that make sense? That's what's called the null hypothesis. That's saying that nothing extraordinary happened. Everything was ordinary. And that's my hypothesis. Okay, then after that comes, after the defense, then comes the prosecution. What does the prosecution do? What does the prosecuting attorney do? What are they
Explains
trying to
why the company is guilty.
Yeah, they say, hey, no, look how many people died. This is not normal. Okay. This number of people wouldn't have died had they not eaten your food because your food was poisonous. Okay. Does that make sense? And the prosecution needs to present evidence to show that the defense is guilty. The defense does not need to present any evidence to show innocence. They just have to say, hey, your evidence showing I'm guilty is not strong evidence. Okay. And I'm giving this because my guess is that most of you have a better feel for this than the way we're going to be talking about it using math. But I want to let you know this is how the math is going to work too. Okay. We're just going to have some equations behind it and stuff. Okay. So that's what happens. And then after that, when you're the jury, after they talk, then who do you hear from? Who are the next people
Witnesses
the
or
witnesses, exactly. The witnesses. So at that point, I like to look at it as the witnesses are giving you the data. Okay, the witnesses are saying, hey, I work for the Department of Health, and normally I only have one person, die with stomach issues, and all of a sudden we got 10. And that is just extraordinary. Okay, that is not normal. I can't imagine it happening from anything other than that or whatever. And then maybe another witness is saying, hey, I work for, Department of Health in the other city, and that happens all the time. Okay. So the point is that you're going to hear the evidence and you're going to look at the probability. Okay. Beyond a reasonable doubt is what they call it. Beyond a reasonable doubt means that you have to make sure that you have such a low probability of this having happened that it just couldn't have happened by chance. You're going to say, no, I think this one really, was the food manufacturer's fault. That's what the idea is. Okay. And then what happens after computing that probability? Then basically the last thing that happens is the jury goes into the back room. Okay. And then they talk. Okay. Now, the back room for us is going to be very different than what you're picturing in a court. The back room for us is going to be the calculator. And so our back room means we're going to calculate and we're going to actually find these probabilities. We're going to look at them and say, hey, is the probability small enough? And if the probability is small enough, we're going to say it's beyond a reasonable doubt. And we're going to say, yeah, that, the prosecuting attorney is right. Or we're going to say it's not beyond a reasonable doubt. We're not going to say the person's not guilty. You're going to say the person there was not enough evidence to show to guilt, not beyond a reasonable doubt. Okay. Now the standard beyond a reasonable doubt in mathematics and statistics is less than 5% chance. Okay. So that's just the standard. Sometimes you adjust that, and we'll talk about that in a bit. But that's the standard beyond a reasonable doubt is less than 5%. Okay. Any questions on that idea? Okay. And then at the end, the jury comes back, right? And then they have to, believe it or not, they elect someone to be in charge of the jury. Okay. And I'll let you know, in my one experience, they made me in charge. So I'm the one that had to talk. I'm the one that had to report it out, as they say. And then they either say, yeah, it was beyond a reasonable doubt, guilty, or we didn't have enough evidence to convict. Do you see how that works? So I wanted to bring that story out because I figured that's something you probably are all somewhat familiar with. I don't expect you to be lawyers. I'm not a lawyer either. But I have been once in a jury. Okay, just let you know. So I actually did experience it. You probably have heard about this stuff. And that's what we're going to do. Any questions on the idea of hypothesis testing? Any questions? All right, so it's very much a step-by-step process. So I have an example, and maybe you were part of it too. And that was on Saturday. This has nothing to do with me being a statistics instructor, by the way. On Saturday, I partook of I was part of Snapshot Day. Have you heard of Snapshot Day? Anyone heard of it? That could be a no. Anyone ever been part of Snapshot Day? Okay, I'm not seeing anyone jumping in. Okay, so what we all did, it sounds like that means no, but I'm not sure. I have no idea because you're not putting it in the chat box or talking. But what we did is every year they find a group of just people in Tahoe, okay, or people who want to come to Tahoe. One of the guy I was working with was actually from Sacramento, and we collect data. Okay, we collect data, and what that meant for me is I went to the Upper Truckee River, if you know where that is, in Myers, and we took samples, water samples, and we took a lot of different samples. I'm not going to get into all the details. And it's just a volunteer. It's not something I get paid for or anything like that. But any excuse to be outside by the river hanging out is a good excuse to me. And it feels good if I feel like I'm, doing something for science. But really, it was just nice to be out. And one of the measurements we took was pH. And I don't know if you know much about pH. pH is how acidic the water is. And it turns out that the pH, so the level of acidic or non-acidic. So it's called acidic or basic. And the pH of water, which is like as not acidic as you can possibly get, kind of the ultra neutral, is 7. So the pH of water is 7. And the idea is 7 is a good pH to have if you want to have a good environment for life. Okay?
Is this accurate?
Yeah. This is accurate. I'm not making anything up.
Just making sure.
Yeah. Now, I'm not, a biologist or anything like that, but I do know, I was a chem minor actually, so I know that piece. So pH of 7 is standard, and it doesn't mean it has to be exactly 7. If it's 6.9999, that's just fine. You wouldn't even notice if you drank some water and it was like that. But if it was pH, if it was a pH of 2, and you put it down your throat, you would have a hole in your throat. It would be awful. Okay, it would be.
Isn't that spicy?
Huh?
Well, isn't that spicy?
Yeah, it'd be worse than spicy. Okay, so here's the thinking. Okay, the question is the average pH in the streams that flow into Lake Tahoe? Okay, does that average differ from 7? Because if it's really far below 7, it's very acidic. If it's very far above 7, it's very basic, and basic is really awful too. Okay, it'll also put a hole in your throat. It's just awful. Okay, and it means life can't be there. Okay, it kills everything. So 7 is like great because that's just pure water. Any questions on the question? Okay, so that's a question that that the scientists have is the pH, the average pH, and the average is most important because if you have a lot of different rivers and creeks flowing into Tahoe, then they all flow in together and they mix. That's how it works. Is that they flow into the lake kind of mixes up because of waves and wind and all that kind of stuff. And if the average is 7, wonderful. If the average isn't 7, not wonderful. Any questions on that? And especially if it's far from 7, but so that is the question that I have for this particular one. And by the way, this isn't just the only thing that's measured. There's a whole lot of measurements, but I wanted to focus on kind of one big example. And the idea is you can do the same kind of thing for all the different measurements we made, but not just pH, but other things like dissolved nitrogen. And we measured a lot of different things, temperature, a bunch of stuff. So pH is the one I'm focusing on. And the question is, does the average pH in streams that flow into Tahoe differ from 7.0? All right, so let me go through hypothesis testing. So the first thing, and this is scientific method, right? What's the first thing we have to do in the scientific method?
Form a hypothesis.
Yeah, we had to form the hypothesis. And the way you form the hypothesis is you write down, just like I talked to you about court, is first we're gonna pretend that is how court works. It's actually the opposite. But first you're gonna hear from the defense attorney. And that is that there's nothing strange. There's nothing bad about Tahoe. We're trying to show it's bad. Okay. Right. We're worried that it's bad. So H naught, that's what we're going to call it. So let me make that pretty. So H naught. Okay. Anyone have a British accent or learn English from Brits?
I learned English from my British father and my Australian mother.
Okay. So you probably didn't learn the word zero first. You probably learned not. Because that's how they say.
I have never met a single on my side of the family. It depends what region, I guess.
Okay, maybe it's a
My
region.
dad's from London.
But okay, so
My
maybe
family's from
maybe it's a
London and Bath.
region. Yeah. I'm not a
Because no
perfect-
one I know says that. No one, even my very pretentious grandparents. That is.
Okay.
That's
Well,
incorrect.
I will tell you the statisticians that developed hypothesis tests first, they were Brits and they used the word not and not zero. So everyone calls it not, just let you know. So if I say H naught instead of H zero, that's because that's what everyone calls it, because the Brits in whatever, region, and that's not my expertise. I don't know region from region. I'd never been to Europe even. So, but I do know that not is a British word, N-A-U-G-H-T, I think. So H naught. And now what we want to look at is the average pH. What letter do we use to represent the average? What letter do we use? Okay, average is mean, but what letter? Okay, so X bar, yes, X bar is an average, but our hypothesis, and this is very important, is not about the sample average. Okay, it's because it's not the sample we're hypothesizing about. We know exactly what the sample was, or we have the data. What we don't know is the population. Yeah, and that's mu. Okay, and that's the Greek letter mu, and that's why I went to this fancy way, because I can show mu. So H naught is that mu equals 7.0. Okay, it's kind of like the defense attorney. There's no problem. It's 7. That's just what it is, of course. Any questions on that idea? I think I'm going to make this a little bigger because it's important. So that's our H naught. Okay, then there's the alternative hypothesis. So again, H naught is kind of like the defense attorney's hypothesis. The alternative hypothesis is kind of like the prosecuting attorney. So the first thing is we write H, and there's actually 2 ways that you'll see this written, and I'm going to use one of them just for now, and that's H1. So if you kind of want to say 1 because 1 is the next number after 0, that makes some sense. Sometimes you'll see it as HA instead of H1. HA because A stands for alternative, and this is called the alternative hypothesis. And then it's still mu. That doesn't change at all. And then now we got to read the question. We want to see if the average pH differs from 7.0. So what inequality right? It's not going to be equal anymore. What inequality do I use to represent this example question? It's very important, by the way. Plus or minus, good try, but plus or minus isn't an inequality. That's arithmetic. I don't see y'all jumping in. Okay, the inequality that we use is not equal to, because the word differ could be, if it's on the low side, it differs. If it's on the high side, it differs, right? Both are bad, right? If you have a pH that's very far from 7, then life won't make it. It's going to kill all the fish, and it's going to kill all the, all the plants and stuff like that that want to be there. So it's not equal to 7.0. Any questions on that? Any questions? Okay, first note, these are called the null hypothesis and the alternative hypothesis. Okay, so these are the hypotheses, that's how you say it plural. And the null hypothesis is the first one, H naught, and the alternative hypothesis is the H1. Okay, and the word null means 0. That's why I use the number 0. Okay.
Wait,
so,
can you say that again? Because you said.
So null is the H naught, and the alternative is the H1.
All right. I thought you said H1, so I wanted to make sure.
Yeah. Sometimes you call it HA instead of H1. That it could be called either way, but you'll see it both ways. Any questions on this idea here? Okay, so that's step 1. Step 1, maybe I'll even write that as step 1. Step 1 is write out the null and alternative hypotheses. Which I just did. Okay, step 2. Okay, step 2 is interesting. Step 2 is consider you're not going to understand what I write, but I'm going to explain it, I promise. Consider the repercussions of a type 1 and a type 2 error. First thing, this is an English word, not a math word. Do you know what repercussions means? Just want to make sure everyone's on board.
Yes.
Yeah. So repercussions are the bad stuff. So some of you don't. So repercussion means the bad stuff that happens, okay, because of the error. Okay, errors are bad, otherwise you wouldn't call it an error. And it's the bad stuff that happens because of this error. Okay, so now let me let you know what these errors are. So type 1 error is the following. Type 1 error means that we reject the null hypothesis when the null hypothesis is true. Okay, which is bad. When you say, hey, it's false, and you were wrong, it was true, that's not a good thing. Is that clear to everyone? Okay, and reject the null hypothesis saying, hey, H naught's wrong, H1 was true. Do you see how that works? But actually, H naught was correct. Okay, so in this case, what that means is that we're going to say, hey, the pH is not 7. Okay. But it was 7. And we meaning, the scientists and the people in charge of everything, policymakers and all that. So if that happens, what are the problems? What are the repercussions in this case? Right? If the pH is not 7, you got a problem, right? It's either like too acidic or too basic. And that's what you're going to say. And you're going to say, hey, it was really acidic or really basic. And there was no issue. It was actually just fine. So what are you going to do? What are the problems with that? What are the repercussions? What's the damage done? Because you announced that, you published it, and everyone is going to go by your word. Any thoughts?
Can you repeat the question?
So what are the repercussions of a type 1 error? And that's the question. All the rest was explaining what that meant.
Potentially.
Mm-hmm.
No, I realized I was wrong.
All right, I don't see everyone jumping in. Well, if you tell all the agencies and you say, hey, I got data, and guess what? We got problems with, all the creeks going to Tahoe. They're too acidic or too basic. We're not sure which one, but it's bad. So what you're going to do is you're going to convince them to put all this money into neutralizing and getting it better so that you don't destroy the environment. And guess what? There was never a problem with the environment. You went in and put all this effort and money into it, and you need to because there was no problem. So that's the repercussions, is we end up putting in, let's go spending a lot of money to deal with the problem, deal with the pH issue. And the pH was 7. So we wasted thousands of dollars. Or maybe hundreds of thousands of dollars. There's a lot of money that goes into environmental protection. Any questions on what a type 1 error does? Have I lost anyone on that idea?
So basically, it's just like the consequence of going against the null hypothesis, like saying that, oh, this isn't true, and then you go about fixing it, and then you find out that there's not actually a problem. Then you
Exactly. And when you do that, you totally wasted a lot of money, time and money, Does that make sense?
Yep.
Yeah, and it's bad, right? It's not a good thing. Now let's talk about a type 2 error. Now, the definition of the type 2 error is kind of the opposite. And that is we fail to reject the null hypothesis when the null hypothesis is false. Okay, remember, you fail to reject. I know that's like a double negative sounding, but it really isn't. It's kind of like saying that we weren't able to find the defendant guilty. It does not mean you found the defendant innocent. Okay. And in fact, in the trial I was on, I wasn't sure whether the defendant was guilty or innocent. Okay. She might have been innocent. She might have been guilty, but it was a might have been. And because it was a might have been, and I didn't see a lot of evidence, we let her go free. Do you see that? So you fail to reject is not, it's not a double negative, actually. It just means you didn't have evidence. You weren't able. So that means you didn't have evidence. So you weren't able to publish it and convince everyone. But actually, the null hypothesis was false. So what are the repercussions? Very different repercussions. What are the repercussions of a type 2 error?
Environmental damage.
Yeah. So what ends up happening is we don't take any action to deal with the pH issues. But the pH is not 7. And we end up with a, let's just call it environmental disaster. I'll call it a disaster. You know, we end up having pretty much, you know, a lot of the species just die out. Okay, and that's bad too. Do you agree? But they're very different. Okay, they're very different errors and very different repercussions in this case, this example. Any questions so far?
Is it okay to say for the second one, like environmental damage is done because the alternative hypothesis is ignored? Or should it be?
It's not that the alternative hypothesis is ignored. It's that we weren't able to say the alternative hypothesis was correct.
Okay.
Different than ignoring. Do you see that?
Yeah.
Right. So for example, when I was, like I said, when I was in court, I was on the jury, I didn't ignore the trial. I just said there wasn't enough evidence to put her in jail. Do you see that?
Yeah.
Yeah. So ignoring is a little different than what this is. This is saying that you don't have evidence to show H1 is true, so you're not able to convince everyone H1 is true. You may still feel it is, but you just don't have evidence, so no one's going to believe you. You don't have empirical evidence on it. And then if no one believes you, no one's going to put money into it. And guess what? You're right all the time, but it doesn't matter because you weren't able to do anything. You weren't able to convince all the agencies to go and fix the problem. Any questions on this step? Step 3. Based on which is worse, decide on the level of significance. Okay, now these are words you don't know yet. So let me kind of explain it from a similarity that we did last week. Do you remember we did confidence intervals and confidence levels? So if you had a 95% confidence level, that means that there's a 5% chance you're misleading people. Is that clear? Okay, so that's what it is. Okay, now it's better to have a higher percent level of confidence because then you have a smaller chance of misleading people. But there's an issue with that because then you're going to end up with a larger margin of error. Similar things happen with the hypothesis test. We're going to have to decide what that cutoff line is to decide to reject. And we can put that cutoff line to 0.00001 as a chance of, of an issue, of a type 1 error. But if you do that, you're probably never going to be able to reject. Okay. On the other hand, if you do a cutoff of say 0.4, well, then you can have a 40% chance of blowing it. You reject it, but you have a 40% chance of being wrong, and that's bad. So it's a, it's a give and take kind of thing. Any questions on the idea before I get into the details? Okay, so let me get into the details, which I do have put, not on this line, sorry.
So like based on which is worse, it's like which consequence is worse,
Yeah,
which error is worse.
yeah, which ramifications are worse?
Okay.
Okay. So let me tell you kind of, and this is this class. It's not just because I'm being, strange or something. I'm doing the most common. Okay, but I want to let you know that there are areas that do things a little bit different. Okay, just like remember I told you 95% is the standard confidence level of confidence. So unfortunately, and don't get mad at me for this, this is just for some reason is the way statisticians have done it, and I don't know why, but with confidence levels, you talk about your chance of being right, 95% confidence. That means you got a 95% good chance of being right, and then 5% chance of being wrong, but your confidence level is 90.95. Turns out, and I have no idea why, the statisticians think backwards, the opposite direction for hypothesis testing. And that is, instead of using 95% chance of being right, they talk about the 5% chance of being wrong. Okay. And again, you could ask me why. I have no idea. I've never heard anyone explain it. Okay. So if type 1 and type 2 error are the same, kind of the same amount of issues and problems, then we're going to use 5% or 0.05. Okay, so if they're the same, we're going to we're going to call it the level of significance, not confidence level. It's now called the level of significance. So let me put that in red because it's some new words. So then the level of significance is 0.05. Okay, and that's the standard number. Okay, again, there's some areas that use different things, but I'd say, most use 0.05 as the standard. Okay, on the other hand, if a type 1 error is worse, then we want to make that chance of a type 1 error much smaller. Does that make sense? So if you're going to want to make it smaller, we're going to use 0.01 for smaller than 0.05. So if the type 1 is worse, in our class, we're going to use 0.05, and they use the letter alpha. That's the first letter of the Greek alphabet. Again, it's standard, so I need to give you the standard letters. And they use the letter alpha is 0.01 if type 1 is worse. If type 2 is worse, then you got to go on the other side. Okay, so the idea is you have a choice whether to have a higher chance of a type 1 error or a type 2 error. So if type 2 error is worse, then instead of going down, we're going to go up. And we're going to use 10% or 0.1. Any questions on that idea? Any questions? Okay, and I want to let you know what these numbers are. These numbers are, they have to do with, as we've seen from the central limit theorem, if you have a large enough sample size and you're talking about means, then we have a normal distribution. So since you have a normal distribution, you can talk about probabilities because we can actually calculate it using the normal calculator. So if you have talk about probabilities, that means we can compute the probability. And if the probability is really small of the event occurring, in other words, that sample mean happening, given the fact that we're assuming the pH was 7, then we're going to say, you know what? Our pH to 7 idea was wrong. And we're going to say we reject the null hypothesis. Whereas if that probability was not that small, then we're going to say, it might be 7 because it's not that unlikely to get what we got if it was 7. And the level of significance is the boundary line. It's that line at which that's where the probability boundary line is. It's our definition of having a low probability. Any questions on this idea? Any questions? Okay, and I just let you know we're going to be doing this for weeks. So it is very important you get this down.
So it can either be only 0.1 and 0.01. It can't be like any other numbers.
Well, 0.05, don't forget, that's the most standard.
Okay.
When you say, can it be? It could be anything you want it to be. But I'm telling you in practice, these are the three biggies that you're going to see almost all the time. Okay. There are some times when you want it to be less than that. When you want it to be, instead of 0.01, maybe you want it to be 0.001. When do you think you would want it to be 0.001? Or maybe 0.00001?
Medical trials.
Yeah, medical trials. If you're going to kill someone, let's say, and in particular, let's say you're doing a medical trial to maybe do some kind of, cosmetic thing, lipstick or something. And we're talking about, is this going to kill someone? You probably want a very, very small level of significance, because 1 in 1,000 chance is not okay if it's just for like pretty lipstick. Does that make sense? So it depends on the kind of medical trial, but that would be an example of medical trial where if there's some kind of, small thing that you're doing for someone, but it's a complete disaster if it goes wrong, then you often want alphas very low. Any questions on that idea? All right, let's look at ours. Okay, for ours, are we going to use 0.05, 0.01, or 0.1? And I want to let you know for exams, the important thing is you explain yourself, because you could go for any of the three. And if you have a good explanation, I'll be up for it. But I want to hear an explanation. So do you think a type 1 is worse? Do you think a type 2 is worse? Do you think about the same? What do you think? Now that we've talked about them. What do y'all think? I'll let you vote on it. Okay, there isn't necessarily a perfect answer. It's not a statistics question. It's a looking at them and seeing which is the worst error. And we've already written down what they are. Total waste of money, thousands of dollars, or environmental disaster. Right? And they're always both bad, but the question is which is worse. Okay. Okay, good. So it looks like you guys are in agreement with me in terms of my philosophy. And my philosophy is we need to take care of the environment. That's my feeling, even if it costs extra money. And that's what we're talking about. So I'm willing to spend a little extra taxes, because that's what we're talking about. Taxes have to go up to make this happen. I'm willing to spend a little extra taxes to make sure we don't have environmental disasters. Okay, but some people aren't. And if some people aren't, okay, then they probably would think the type 1 is worse. But I think the type 2 is worse. Okay, so I'm going to go with the majority of at least those who put in the chat box. And we're going to, so we agree here that, too many E's, that the type 2 error is worse. So we will choose 0.1 as the level of significance. Okay, any questions on that? Okay, and as I kind of inferred last week, when I did some consulting work for the Forest Service, so it actually meant something instead of like this, we're just kind of, doing it as a class, but it actually meant something for the Forest Service. They used a 0.1 for these kind of things because they agreed with us is that environmental disasters are worse, and it's worth spending a little bit of their funding to make sure the environmental disasters don't happen. So they use the higher level of significance. Any questions on that? Okay, that's step 3. Okay, step 4. Okay, and I want to let you know, step 4 is the hardest step of all of them in the real world. Any guess on what step 4 is?
Interpreting the results.
No, that's not that hard at all. No, this is hard. Okay, it's easy to type, by the way. but it's hard to do, and that is collect the data. Okay. All right. So, you know, we got 20 years of data. We're talking a 20-year project, hundreds of volunteers. Okay. And not just hundreds of volunteers, but you got to have the organizers, they get paid. That's a lot of work. Okay. Whereas step 1, 2, and 3, we did in class. And that took what, 45 minutes. Okay. Whereas step 4, 20 years of work, 21 actually so far. So collect the data. Again, it's so easy to write. It looks so easy, but in the real world, that is what all the work is collecting the data. So there's not a whole lot to say about it, is you collect the data. And I was a helper on collecting the data on Saturday. Okay, any questions on step 4? Again, that one would take forever to explain exactly how to collect the data. That's all science and stuff and not statistics. Any questions on that at all? Okay, step 5. Step 5 is calculate the p-value, which is the probability that if H naught is true, and we use that sample size, that we will get an as extreme or more extreme results as what the data should have. Okay, so I'll go over that in more detail because it's a lot of words and can get confusing. But what I want to show you is the data. So we got to calculate that probability. How do you think we're going to calculate the probability in our class? At this point in class, you should all know. Yeah, we're going to use a calculator. Now, I don't know if you remember, but there are 2 types of calculators that we've used in our class. There is the LibreText calculator that I programmed. And then there's the one that you use for the project 1, which you're going to use for project 2, by the way, also. For this particular example, I need to use the one we use for the project. And the reason is that we're talking about 21 years of data. Way too much data for the little simple calculator I did. So I needed to use a full spreadsheet program. So let me show you what that looks like. And in fact, I emailed Emily saying, do you have the data? I would love to use it in my class so we can talk about it. And she sent me an Excel spreadsheet, and I copied and pasted it into column A. And you'll notice, by the way, N is 583. Okay, this is not some minor task to collect data like that. Okay, 583 samples have been collected. This is a big data set, very large sample size. Any questions on that? Yeah, each of the river, and it's 20 years of work, 21 actually. So it's 21 years of measurements in all the different rivers and creeks that go into Tahoe. That's a lot, just let you know that. Okay, so the good news is we have a giant sample size. So we need to do a few things in this calculator. One is we have to decide H1. It wasn't a less than, right? It was a not equal to. The other is this mu naught, That's what's on the other side of the H naught. In this case, it's not 12, it was 7. And that's it. Any questions on this calculator? This spreadsheet program? And I programmed this one too. But this works better when you have hundreds of data values. Okay, so let me tell you a few things. One, you might recognize this letter T. T, you remember the student's T distribution? It's the same. So it turns out that this involves the student's T distribution. Because we're looking at the central limit theorem, we don't know the standard deviation for the population. So we have to use the T distribution to make that approximation. Okay, and that we call this the test statistic, which is about negative 2.9. And then the p-value, that's the important number. The p-value is about 0.004. Okay, rounded to 3 decimal places. So let's write that out. So in our case, our p-value was equal to 0.004. Okay, so we just calculated the p-value. Any questions on that so far? All right, the p-value is 0.004. So now the next step, step 5. Compare the p-value with the level of significance. If p is less than alpha, reject the null hypothesis. If p is greater than alpha, fail to reject the null hypothesis. Any questions on step 5 in this case? I'm on 6, sorry, 6. Sorry about the steps. That wasn't supposed to be a trick question, that was a typo. So any questions on step 6? Okay, well, in our case, our p-value was 0.004. Which is certainly less than 0.1, which was our alpha. And by the way, even if we had chosen 0.001, it's still less than. Okay, but you have to choose before you collect the data, not after. That's important. The order at which you do things is necessary. You can't change the order. Any questions on that? So step 7, state your conclusion. So in this case, here's the way you write it. There is statistically significant evidence to conclude that the population mean pH of water flowing in Lake Tahoe is not equal to 7.0 or differs from 7.0, same thing. Any questions on the conclusion? I have a tougher question. Does that mean we have a disaster? What do you think? And the evidence is strong. Do you think we have a disaster?
Yes.
Okay, one more guess. The answer is no. Okay, we know that the pH is not equal to 7. Okay, but if you go and look at this, it turns out that our mean was about 6.9, which I forgot to put in the chat box, but that's what you guessed, and it was 6.9. So the mean was 6.9, and 6.9 is actually not that far from 7, it turns out. So that's not disastrous. Okay, it just means that it's not perfectly 7. All right. So, you could change it, for example, to say, well, you have a problem instead of, 7. Well, maybe you have a problem if it's acidic, maybe less than 6.5 or something. And then you would have gotten a giant p-value, it turns out. So again, that's where the scientists have to come in. And I'm not going to pretend to know what that borderline, what that special line of danger is. But I will tell you, what we say is that it is statistically significant that it is not equal to 7, but it may not be what's called practically significant. Practically significant tells you how far you are away from 7. What have we already done to talk about how far you are away from 7? Hint was last week. Hint, hint. Yeah, I'll go back to the conclusion in a second, but what's the big topic that helps you talk about how far you are away instead of are you less or not equal to? This is very important. I don't see y'all jumping in. Last week, we spent pretty much the whole week doing it. And we will go back to the conclusion. But what did we spend all of last week doing? Yeah, confidence interval. Not just for proportion, mean also. So in particular, this calculator does a confidence interval. And this goes from 6.8 to 6.96 or so. So the question is, and this is where I'm not qualified to tell you, because I have no idea, is a 6.8 a bad, is that like too low or not? And that's where scientists come in. And I'm not a biologist, so don't ask me. But we can look at the confidence interval that kind of doesn't say, is it less than 7? But that would be, what is the range that we see it to be in? Do you see the difference? So hypothesis testing and confidence interval are very different. So now I'll go back and here's the conclusion. What I want to do is I'm going to take a 5-minute break. It's 5:09, and I try to take a break a little earlier, but I'm going to let you take a break. I could leave it up like this, but let me Okay, it's been 5 minutes, so let's get back. Hopefully you had a little bit of a break. I think it's important. So let's take a look at a few things. So I just wanted to note, and this is important, this state the conclusion, that is the main piece of the whole hypothesis test. This is what you definitely don't want to get wrong, because this is what you use to make the decisions. This is everything. All the rest is little details. This is the biggie, is to get this conclusion right. And you don't want to state it backwards, because then you're going to do the exact wrong thing you're supposed to do. So in this case, I want to mention a few things. There is statistically significant evidence. Those are important words, and that comes up a lot. Another couple important words are population mean. We saw that with confidence intervals. Population mean, it's not the sample we're talking about. We're really talking about the entire population of all inflows into Lake Tahoe over 21 years we're talking about. So again, all we have is a sample. We don't have the whole population. But what we have is we have evidence, statistically significant evidence about that population. Any questions on step 7? It's a biggie. Maybe I'll even make it even bigger, because that's how important it is. So what I want to give you a little warning or heads up is, don't get step 7 confused with step 8 and 9, which are much less important. And if I ask you to write down the conclusion and you write down step 8 or step 9, that's not good. You need to write down step 7 for the conclusion. Okay, what can you be concluded? Then this is step 7. So now I'll move into step 8. And step 8 is let us interpret the p-value. Okay, so the p-value was 0.004, or about 0.4% as a probability. And that is a probability, so it's the probability of something happening. And here's the way we write it. So what we can say, and I kind of mentioned it already, kind of the idea of it, and now let's write it in context with the number 2. So what we can say is that if the population mean pH of water flowing into Lake Tahoe is 7.0. Okay, so if H naught is true, that's what I just wrote down. And if we sampled another, and now let me go back to this. There were 583 in our sample size. Again, very big sample size in this case. Another 583 samples of inflow. Then there would be a 0.4% chance. Okay, our p-value is 0.04. So 0.4% chance that this new study would have a pH of either less than, and now again, if we look at the sample mean, that was about 6.9. Or greater than 7.1. Let me ask you, anyone have an idea of how I got 7.1? This is usually the hard part of these kind of questions, is getting that 7.1. It's not hard if you know how to do it, though. Yeah. Well, your idea was right, Jack, but 0.1, not 1. I think that's what you meant though, right? So 6.9 is 0.1 below 7. 7.1 is 0.1 above 7. For our particular test, if you go back to the hypothesis test, this is very important. We have a two-tailed test. We have a not equal to, which means we have the left side and the right side, which will make H1 true. So the left side is the 6.9 or below, and then we look at the mirror image, and the right-hand side will be the 7.1 or above. So in particular, that's why we get the less than 6.9 or greater than 7.1. Another way of saying the same thing is it would differ from 7 by at least 0.1. It's another way of saying exactly the same thing. Any questions on step 8? Okay, step 9. Interpret the level of significance. Okay, now our level of significance was 0.1. So what is that 0.1? Well, 0.1 is a probability, and it turns out it's the probability of a type 1 error. So what I'm going to do is I'm going to copy and paste the beginning, first half of the interpretation of the p-value. Just to emphasize, it starts out exactly the same. And that is if the population mean pH of water flowing into Lake Tahoe is 7.0, and if we sampled another 583 samples of inflow, then there would be A. And now our level of significance was 0.1 or 10% chance or probability. Maybe I'll write probability. And now what a type 1 error means is that H naught was true. That's if the mean pH of water was 7. Then we'd end up thinking that it was false. So thinking that it's false means that we've concluded, well, falsely conclude that the pH of water flowing into, and let me write down the population mean because that's important. pH of water flowing into Lake Tahoe differs from 7.0. That's pretty much restating the type 1 error. It's the probability of a type 1 error. So are there any questions on step 8 or step 9? Okay, and I want to mention one of the big mistakes that I see a lot is I ask, what is the conclusion? And you give me step 8 or step 9, which isn't right. The conclusion, step 7. And that's the main thing. In terms of test questions, you will always be asked for step 7 for a hypothesis test. And step 8 and step 9, I almost never will will ask more than once on a whole test for the step 8 and step 9. Whereas step 7, you're going to see multiple times. So that's just a note. I don't ask you to do every step, but step 7 is the biggie. That's the punchline. And if you can't write the punchline, then what's the point of doing hypothesis testing? So step 8 and 9 are kind of details, but they're important little details. Any questions at all on this example of hypothesis testing? Any questions? Okay, and I want to let you know the order at which you do the steps are important. Okay, that is important. You can't switch them. So I wrote some templates for you guys. So the p-value interpretation template is if, and I put the null hypothesis true. So in our case, if the pH, population mean pH of inflow is 7.0, that's the null hypothesis being true. And another sample of XXX, in this case, it was 500 and something 8 samples, was taken. There would be and then the p-value probability. So in our case, it was a 0.4% probability that, and then the results of the new study would be at least as extreme as the results of this study. In our case, it differed by at least 0.1 from the 7 pH, or it was less than 6.9 or greater than 7.1. And the level of significance template starts out the same way. If, and then the null hypothesis is true, but don't write the null hypothesis true. Write down what the null hypothesis says. And if another sample of whatever our sample size was taken, there would be and now it's a level of significance probability. In our case, it was 10% probability that the new study would result in falsely concluding that, and then you write the alternative hypothesis is true, not those words. In our case, it was falsely concluding that the pH differed from 7. Population mean pH differed from 7. So those are some templates that might help you out that work for pretty much all hypothesis test questions. Okay. Any questions about the templates? Any questions? Okay, so if you don't have any questions, let's look at another example. I think it's very important to see a lot of examples. And did I have it above? Yeah, let's look at this one next. Okay, so suppose that you want to see if women are drinking less than the recommended 2.7 liters per day on average. Okay, so now, what's H naught? That's step 1, right? Is write H naught. So H naught colon, and then what's H naught in this case? It's not a trick question or anything. This isn't supposed to be too hard.
2.7.
Yeah, what about 2.7 though? I'm looking for a fancy Greek letter. That's a hint.
Mu.
Yeah, mu equals. So mu equals 2.7. Okay, every symbol I have written down must be there or you lose points. So H naught colon mu equals 2.7. Once you get used to it, it won't be that hard. What's H1? I'll start it out, mu. And then what? This is a matter
Less.
of, yeah,
Less
we
than
have
2.7.
yeah, because we want to see if it's less than the recommended. So that means that mu is less than 2.7. So this is what's called a left-tailed test because we're going to reject H naught if mu is far to the, if our, X bar is far to the left. Any questions on that? So there's H naught, there's H1. Okay. For this particular one, how about a type 1 error? What are the ramifications of a type 1 error? So what are the bad things that happen if type 1 error happens?
Well, you'll say that they're drinking less than they're supposed to, even though they are.
Okay, so that's kind of the definition of a type 1 error. And then what bad things will happen because of it?
You'll recommend more that they'll drink more water when they don't have to.
Yeah, we're going to push women men to drink more water when they are already getting enough water. Okay, we're going to make them feel bad. Right? Because we're going to say, hey, look, you're not doing things right. You need to drink more. You're just not there. You need to get better. And they're going to feel like they're, not doing things right in terms of their health. But they're actually doing perfect on their health when they are very healthy in terms of fluid. In terms of drinking enough. Okay. And that's bad. Okay. It's not like you're probably not going to kill anyone that way. And then there's a type 2. So type 2 is kind of the opposite. What are the ramifications of a type 2 error?
You'll say that they're healthy even though they're not drinking enough water.
Not
So,
quite. So be careful about saying they're healthy.
you'll say that
We'll say nothing. That's the problem.
do
you see? Okay, we don't have any evidence. We're just not going to say anything. We're not going to say they're healthy because that would be saying that you accept H naught. You never accept H naught. You only fail to reject. So we won't suggest that they drink more. But they're not drinking enough. So, and I'm not a doctor or anything, but so whatever health ramifications, health problems from not drinking enough will continue. Any questions on this? Okay, both of these are bad. Hopefully you agree. And again, I'm not here to say which is worse because that depends, on the way you think about things. Okay, but let's suppose we just go with standard for now. So let's say that they are about just as bad. Right? Giving people psychological problems or giving people physical problems, they're both bad. So in that case, if they're just as bad, what do we use? What's our level of significance? So you remember? So what's the level of significance if type 1 and type 2 are equally bad?
For type 1, it's 0.01, and for type 2, it's 0.1.
No, but if they're just as bad, what do we use? So let me write since.
I thought that was it.
Oh, no. The first piece was they're the same. Remember? What's the standard? Very important. 0.05, 5%. That was what you do if they're type 1 and type 2 are pretty much similar in terms of being bad. Okay, they're never the same things, but the damage done could be just as severe. And I'm just going to pretend we're worried just as much psychologically as physically. Any questions on this? Okay, once we've done that, then we're going to get into our calculator. And here's the data. Okay, and I do want to give you a disclaimer. Unlike the last one, the last set of data I showed you, that was real data. Okay, that I actually got from the Keep Tahoe Blue organization that collects the data. Okay, they're the ones that, though they keep the data, I help collect it. These numbers here that I highlighted, I just made them up. So please don't, use them for anything. But we're going to pretend because it's just a class, we can do that. And here's what I'm going to do. I'm going to copy it. And now we're going to go to this calculator, kind of the one we've been using, the one that's going to be on tests and quizzes. And which one do you think we're going to use? What number? So what number test are we going to use for this particular example? Yeah, this one's number 15. It's hypothesis test for a mean with data. We're doing a hypothesis test. We had an H0 and H1. That means hypothesis test. We had a mean because of the mu, and it was just one mean. And then we had data. It was a big, long list of numbers. So I'm going to click on that. Okay, and hopefully you're used to this at this point. You put in the numbers separated by commas. It's a long list, but I just copy and pasted. Any questions on that? Okay, just let you know, I didn't used to have this sigma here because I thought it was a waste of time, but a lot of other faculty wanted it there. In our class, sigma will never be known because in the real world, it never is known. So leave it blank. Got it? So the sigma is just left blank. And that would be if you knew the population standard deviation, which never happens. I've never seen any real world examples where you know it. Okay. On the other hand, is it less than, greater than, or not equal to? Hopefully you all know if you remember.
Yes.
Yeah, this one's a less than because that was our H1. H1 was that mu was less than the number. And then it says mu naught. Now, again, mu naught is going to be what's on the other side of H0 and H1, which was 2.7. So mu naught is 2.7. Any questions on that? And then I hit calculate. And it gives us all kinds of things. It gives us our X bar. It's always nice to know X bar. The sample mean was 2.54. It gives us the test statistic, which was negative 1.94 or so. It's a T, as I mentioned, students t-test. It turns out same as what we have with confidence intervals. It gives us the p-value, which is about 0.03. So the important thing is p is equal to 0.03, and that is less than 0.05. So what is the conclusion? And you want to get used to not just listening to me, but you want to get used to writing it out. So I'm going to give you just a minute or two. I want you to write it out before I write it out, and then you'll see. And hopefully you get the right thing. So see if you can write down on a piece of paper, or you can type it out, whatever, what the conclusion is. Maybe I'll do that. And that way you can see everything. So I'm going to give you a minute or two to write out the conclusion. Because that's the biggie, the punchline. And I do want to let you know, I made up these numbers. So, don't quote me. The 2.7 I didn't. That one I actually looked up. According to Google, 2.7 was what the recommended number of liters that women are supposed to drink is. And men are supposed to drink a whole nother liter. Not sure why, but men are supposed to drink more. 3.7, it turns out. Okay, hopefully you've had enough time. So let's write it out. What are the first few words? Put in the chat box the first few words. So what's the first few words of the conclusion for every conclusion? The first three words is always exactly the same for all hypothesis tests, no matter what the result. So put in the chat box the first few words, make sure you remembered them. Can you remember? Don't remember? All right, maybe I'll do it then. I don't want to wait forever. It's just a few words. There is. That's the first two words. So sometimes it helps to have the first two words in your head because that way it'll get you started. And the next word is always statistically. And then the one after that matters and it changes. If you have P is less than alpha, it's significant. Okay, on the other hand, had P been, say, 0.37 or something, then you would say insignificant. That's the only thing that changes is that IN. There is statistically significant evidence to conclude that the population mean amount of fluid that women drink is less than 2.7 liters per day. Any questions on the conclusion? Let me make it a little bigger because it's so important. Any questions at all on the conclusion? Okay, so you definitely want to practice so you get these down. Okay, again, the first three words are always exactly the same. The fourth word is either going to be significant or insignificant. And the fifth word is always going to be evidence. And even to conclude that, that's always the same. We're going to see on Thursday that population mean isn't always going to happen. Sometimes it's going to be population proportion. Just like we had for confidence intervals, that'll happen and that'll be Thursday's task. But today I'm sticking to mean because we have all Thursday to talk about more stuff. Any questions at all about this conclusion? All right, instead of typing it out, because I want to convince you that the conclusion is a biggie, and if I type everything out, you may not remember what's big and what's small. So I'm going to just say it in terms of interpreting the p-value. So to interpret the p-value, again, it's the template. And I'm going to kind of use the template. And that says that, remember, if the null hypothesis is true, null hypothesis is that mu equals 2.7. So if the population mean amount of fluid that women drink per day is 2.7, and if we surveyed another, and I forgot how many there were here, 1, 2, let's say, I don't know, 35 or so. I don't remember exactly how many I put in, but if we surveyed another 35 women, then there would be a 3% chance, that's our p-value, that the sample mean for the new study would be smaller than what we got, and what we got again was 2.5. So it would be smaller than 2.5 if you want 2.54. And that's the interpretation of the p-value. Okay, if you want to interpret the level of significance, then we would say we start exactly the same. If the population mean amount of fluid that women drink per day is equal to 2.7 liters. And if we surveyed another 35 women, then there would be a 5% chance, there's our 5% right here, a 5% chance that the new study would lead us to falsely conclude that the population mean amount of fluid that women drink per day is less than 2.7 liters. Any questions on interpreting the p-value or interpreting the level of significance? Any questions on that? Okay. Do you think this is used ever? Or is this just some kind of little thing? This kind of stuff. I don't see you all jumping in. Hopefully you're paying attention. Okay. So the answer is, if you are ever going to try and publish a research paper in just about anything, then you're going to be doing a hypothesis test. It's just part of it. And a lot of times, since you're writing it to an audience that totally understands it, you're going to write it in higher level language than what we're talking about, but you're going to be running a hypothesis test. It turns out it's kind of weird in terms of disciplines where the PhD, to get a PhD, and then you got to do this full research. As far as I know, there's only one discipline where you don't do a p-value. Any guess? In terms of research papers, there's really only one discipline where you won't see a p-value in research. And it's very ironic. That's a hint. If you don't know, the discipline is math. Okay, mathematics, you have to prove something, and you have to be 100%. It has to be 100% that you got it right. There's no such thing as, well, there might be a 5% chance that I'm wrong. No. In math, it has to be right, but in every other subject, you collect data And then you say, well, you know, with a p-value of whatever 0.03, I can say that I have evidence. So it turns out math is the only one that you don't do that. Every other subject you're doing data collection. Math is all proofs. It's different. So it's kind of weird, and I'm teaching it, but you know, my dissertation didn't have a p-value. But everyone that I've read, and I've read a lot of people's dissertations, former students, they all do hypothesis testing and p-values. Every one of them. Okay, just to let you know how important this is. Okay, and I'm not just saying for just PhDs, but pretty much any paper that's published that isn't a math paper. So I'm looking at the time, it's 5:50, and I'll let you know next time we're going to move to proportions, and it's actually not that much harder than, in fact, I don't think it's harder at all. It's the same. And we'll do proportions. We'll also have some pictures. And even more, we'll talk about the project. So for now, I'm going to stop the share. And I'm going to stop the recording.